A modern house can look perfect on paper and still fail. The night winter turns cruel. The heat is on. The system hums. Bills climb. Yet floors stay cold. Rooms drift apart. And a draft pulls warmth out faster than it arrives. We accept this as normal. Now place that beside the Frontier. Not the painted version, but the working one. Weeks of deep cold. No backup fuel. No margin for mistakes. Cabins built with hand tools and raw timber endured minus 30 degrees Fahrenheit nights with a single fire. No insulation rolls, no membranes, no sealed windows. That contrast raises a quiet question. What did frontier builders understand through use, not theory, that we quietly abandoned? This video isn't nostalgia. It isn't about comfort. It investigates one system only. How frontier cabins kept heat from escaping under extreme cold, and why many modern homes waste it. We'll follow the logic step by step, where heat actually leaves, how small choices compound, and why the old approach worked until speed and convenience replaced it. If you want investigations like this, comment, like, and subscribe. Modern houses are designed around a simple promise. If you add enough material and enough energy, warmth will follow. Thicker insulation, bigger footprints, more rooms, more output from the system in the basement or on the roof. For most of the year, that promise seems to hold. The house feels acceptable, quiet, controlled. Extreme cold exposes the flaw. When temperatures plunge far below normal, the problem is no longer how much heat a home can produce. It's how fast that heat escapes. Rooms begin to separate into warm and cold zones. Floors pull heat from your feet. Drafts appear where none were noticed before. You can feel the outside pressing inward, even when the heat has been running all day. What's striking is that the discomfort isn't evenly spread. Some rooms feel tolerable, others feel abandoned. Corners chill first, lower levels suffer more than upper ones. The system keeps working harder, but the comfort it produces shrinks. This is the point where modern thinking usually turns toward addition. More insulation, a stronger heater, sealed windows, another layer of material. The assumption is that warmth is something you generate and push into a space until it overwhelms the cold. But that assumption hides the real problem. Heat does not vanish uniformly. It leaves through specific weaknesses, through moving air, through openings that seem minor until pressure and temperature differences turn them into exits, through volume that is too large to manage once the cold settles in for days instead of hours. Modern homes are built for average conditions. They perform best when energy is plentiful and the weather behaves. In extreme cold, they rely on constant input to maintain balance. When that input slows, or when the cold persists longer than expected, the system shows its limits. This is where the comparison becomes uncomfortable. Frontier cabins were smaller, rougher, by modern measures, poorly built. Yet they remained livable in sustained cold that would overwhelm many contemporary houses. The difference wasn't better materials. It wasn't stronger fires. It was focus. Frontier builders weren't trying to make more heat. They were trying to stop losing explaining warmth at the points that mattered most. To understand why modern homes struggle, we first have to understand what frontier cabins were actually built to resist. Frontier cabins were not built for comfort. They were built for conditions that left no room for failure. Across much of the northern frontier, winter temperatures did not arrive in short bursts. They settled in. Weeks below zero were common. In many regions, minus 20 degrees Fahrenheit was ordinary, and minus 30 degrees Fahrenheit was not exceptional. When cold behaved that way, it stopped being weather and became a constant force pressing against everything that leaked heat. Fuel was the first hard limit. A frontier family could not burn freely. Cutting, hauling, and splitting firewood took enormous labor, and forests were not always close. Historical accounts describe winter wood piles measured carefully, because running out was dangerous. A cabin that required constant roaring fires would empty its fuel supply long before winter ended. This meant the problem was not how hot a fire could burn, but how long warmth could be held after the fire settled down. Cabins were often small by necessity. Many measured no more than 12 to 16 feet on a side, with a single room serving every function. Ceilings were low enough that heat did not drift upward into useless space. Every extra cubic foot of air had to be warmed and then kept warm. Anything larger worked against survival. Nighttime was the real test. Fires were banked low or allowed to burn down entirely to conserve fuel. If the cabin lost heat quickly, the interior would approach outdoor temperatures by morning. Records describe frost forming inside poorly sealed shelters. Cabins that worked stayed above freezing even after hours without active fire. Isolation amplified the stakes. There was no repair crew, no replacement materials arriving midwinter. Cracks had to be sealed by hand, doors had to fit, openings had to be controlled. A mistake made in autumn could become a life-threatening problem by January. This environment shaped priorities with brutal clarity. Frontier builders didn't ask how to heat a space faster. They asked how to make a space resist cold for as long as possible. The cabin was not an expression of taste. It was a container for warmth, expected to perform every night, for years, under the worst conditions winter could deliver. That pressure explains why their solutions look different. And why the first misunderstood element is the walls. There's a simple explanation people reach for when they look at an old cabin. Thick logs must have kept it warm. The image feels right. Heavy timber, solid walls, a sense that mass alone held back the cold. It's only partly true. Logs do slow heat loss. A wall made from solid wood performs better than thin boards. But the numbers don't support the idea that thickness alone explains survival at -30 degrees Fahrenheit. Many frontier cabins used logs between 8 and 12 inches thick. By modern standards, that isn't exceptional. On its own, a wall like that would still bleed heat steadily over long winter nights. Yet those cabins didn't fail. The reason is that cold doesn't attack a building evenly, and heat doesn't leave evenly either. Most heat loss doesn't seep gently through every inch of wall. It rushes out through specific weak points. Gaps, cracks, openings where air can move. Frontier builders understood this through experience. They didn't treat walls as static barriers. They treated them as living parts of the structure that changed over time. Freshly stacked logs shrank as they dried. Seasons shifted them. Wind worked into seams. Cabins settled. None of this was unexpected. That's why walls were revisited constantly. Chinking wasn't a one-time job done at construction. It was seasonal maintenance. Clay, moss, lime mixtures, or whatever local material was available were pressed into gaps as they appeared. Accounts describe cabins being resealed before winter, then touched up again mid-season if cold air could be felt along the walls. Not because the logs were failing, but because small openings mattered more than the bulk of the timber around them. A single gap the width of a finger could leak more heat than several square feet of solid wall. That's not intuition. That's what cold air does when pressure differences build up between inside and outside. The colder it gets, the harder air tries to move. This is why frontier cabins often felt warmer than their size suggested. The walls were not perfect. They didn't need to be. They needed to be tight where it counted. Thickness helped, but control mattered more. Once you see that, the focus shifts away from wood entirely. Because if walls weren't the main defense, the real enemy had to be something else, something invisible, something far more aggressive than cold surfaces. Cold walls feel threatening, but they are not what empties a cabin of warmth the fastest. Moving air does that. Anyone who has stood near a draft understands this instinctively. The temperature may read the same, yet the space feels colder the moment air begins to move. That sensation isn't psychological. Flowing airstrips heat away far more efficiently than still surfaces ever could. Frontier cabins were not airtight by modern standards, but they were controlled. They had fewer places for air to enter and fewer paths for it to escape. One room, one door. A small number of windows, often no more than 1 or 2, and usually placed where wind exposure was lowest. Doors were heavy, built from thick planks, and fitted tightly because a loose door meant constant heat loss. Windows were small not because glass was rare alone, but because every opening weakened the shell. Some cabins relied on oiled cloth or animal hide instead of glass, materials that flexed with the frame instead of cracking and opening gaps. The most important detail was maintenance. Sealing the cabin was ongoing work. Chinking, packing material into the seams between logs, was not decoration. It was life support. When temperatures dropped sharply, people could feel where air was sneaking in. Those spots were addressed immediately. Clay, moss, rags, even snow in emergencies. Anything that stopped airflow mattered. This focus paid off. In cold conditions, even a small opening can exchange a surprising amount of interior air in an hour. Multiply that by a long winter night, and a loose cabin becomes a cold one regardless of how thick the walls are. Frontier builders didn't fight air everywhere. They fought it where it moved. Corners, seams, door frames, window edges. The rest of the structure could be imperfect and still perform, as long as those paths were controlled. This is where modern homes often struggle. Large interiors create pressure differences. Multiple rooms pull air in different directions. Ducts, gaps, and connections multiply exit points. The heating system compensates by pushing more warm air into the space, but the leaks remain. Frontier cabins took the opposite approach. They limited airflow first, heat second. Once air movement was restrained, something important happened. Warmth stopped racing away. It began to linger. And that brings us to the next realization: why the size and shape of the cabin mattered just as much as how tightly it was sealed. Frontier cabins were small for a reason, and that reason wasn't just limited resources. It was control. A larger space is harder to keep warm not because it needs more heat, but because it offers more ways for heat to escape. Every extra foot of air has to be warmed, held, and defended. In deep cold, that becomes a losing battle. Frontier builders learned this quickly. Cabins across the northern frontier often clustered between 150 and 300 square feet. That wasn't coincidence. It was the smallest volume that still allowed people to live, work, and sleep without wasting warmth. Ceilings were kept low, not cramped, but contained. Warm air naturally rises, and any height above what was usable became a reservoir of wasted heat. A low ceiling kept warmth where people actually lived, at head and body level, not hovering uselessly overhead. The single-room layout mattered just as much. One fire heated one space. There were no hallways pulling warmth away, no unused rooms absorbing heat and giving nothing back. Everything happened within the same thermal envelope. Cooking, sleeping, repairing tools, drying clothing, all of it benefited from the same retained warmth. Contrast this with modern interiors. Multiple rooms divide heat into compartments. High ceilings pull warmth upward. Long distances between heat source and living space create constant loss. Modern systems attempt to solve this by distributing heat aggressively, pushing it through ducts and vents, hoping it arrives where it's needed before escaping again. Frontier cabins avoided that problem entirely. They didn't distribute heat. They contained it. The shape of the cabin reinforced this logic. Simple rectangles or squares, few protrusions, minimal surface area relative to interior volume. Every design choice reduced exposure. The structure didn't fight winter across dozens of surfaces. It presented a compact target. This containment allowed a single fire to do something remarkable. Not heat a room briefly, but warm the space itself. Walls, floor, furnishings absorbed warmth and released it slowly. Even after the fire settled down, the cabin resisted the cold for hours. Once heat was contained, frontier builders could afford to be gentle with fire. This is another place where modern assumptions mislead. We imagine frontier life as a constant battle against cold, fires roaring day and night. In practice, that would have been unsustainable. Wood was finite, labor was exhausting. A fire that burned hard burned fuel fast and created sharp temperature swings that worked against the structure. Frontier fires were usually steady, not aggressive. Smaller loads, slower burns. The goal wasn't to flood the cabin with heat all at once, but to let warmth soak into the space itself. Thick hearthstones, packed earth floors, and solid furnishings absorbed heat over hours. When the fire settled, those surfaces released warmth back into the room. This mattered most at night. In many cabins, fires were banked low before sleep or allowed to burn down entirely to conserve fuel. Cabins that relied on constant high heat cooled rapidly. Cabins that had warmed their structure cooled slowly. Accounts describe interiors remaining above freezing by morning even after hours without active flame, while outdoor temperatures stayed far below zero. There's also a mechanical reason this worked. Gentle heat created less forceful air movement. When fires roared, hot air rushed upward and out, pulling cold air in behind it. Slower burns reduced that pull. Heat stayed put. Smoke moved predictably. Drafts were manageable. Modern systems do the opposite. Forced air heating pushes warmth aggressively, cycling on and off, creating pressure changes that drive air through every small opening. Comfort depends on constant motion. The moment the system pauses, heat begins to flee. Frontier cabins didn't need constant motion. They needed time. This approach paid off during fuel shortages, illness, or storms that prevented cutting wood. Cabins that had been steadily warmed could ride out interruptions. Cabins that depended on high output could not. The proof isn't theoretical. These structures were lived in for years, sometimes decades, through repeated winters. The system worked not because fires were stronger, but because they were restrained, used to charge the space, not fight the cold directly. Which raises the final question. If this approach was so reliable under extreme conditions, why did it vanish so completely? The frontier cabin didn't disappear because it failed. It disappeared because the world around it changed. As settlements grew, priorities shifted. Speed mattered more than endurance. Houses needed to go up quickly to support expansion, trade, and growing families. Larger homes became symbols of stability and success, even in climates that punished excess space. New materials promised convenience. New systems promised control. Heating followed the same path. Instead of shaping buildings to resist cold, design began to assume that heat would always be available. Coal deliveries. Later, oil. Then gas and electricity. Warmth became something you produced on demand, not something you carefully guarded. This changed how houses were built. Rooms multiplied. Ceilings rose. Windows grew larger. Walls became thinner but more uniform. The responsibility for comfort moved away from the structure itself and onto the heating system. As long as fuel flowed, the house could stay warm. That trade-off made sense in a world of reliable supply. It reduced labor. It simplified construction. It allowed flexibility in layout and appearance. But it also created dependence. When heat production became the solution, heat loss became easier to ignore. Over time, this logic hardened into standard practice. Homes were no longer expected to hold warmth on their own. They were expected to cooperate with machines that would constantly replace what escaped. The idea of designing for the worst night of the year faded. Average conditions became the benchmark. The consequence is subtle but important. Modern homes often perform well until something interrupts the system. A power outage, a fuel shortage, an extended cold spell. When that happens, they shed heat quickly because they were never meant to hold it for long. Frontier cabins demanded more patience, more maintenance, more restraint. They asked builders to think carefully about size, openings, and airflow. In return, they offered resilience. They could endure pauses. They could coast through the night. What was gained in speed and convenience came at the cost of that endurance. And it wasn't obvious at first because as long as energy stayed cheap and available, the weakness remained hidden. Only when systems fail do we notice what was quietly traded away. What makes the frontier cabin worth revisiting is not how old it is, but how consistently it performed. These structures were not experiments. They were lived in through decades of winters. Some cabins sheltered multiple generations. Others were abandoned only when families moved on, not because the buildings failed. In regions where temperatures routinely stayed below zero for weeks, cabins that followed the same basic principles, small volume, limited openings, controlled airflow, steady heat, remained usable year after year. The lesson isn't that frontier builders were smarter in some abstract sense. It's that their priorities were different. They designed for the worst conditions first. If a cabin could hold warmth through a negative 30 degrees Fahrenheit night with a low fire and a finite wood pile, it would handle everything else easily. Modern homes often reverse that logic. They are optimized for comfort during normal conditions and supported by systems meant to correct weaknesses after the fact. That works, until it doesn't. When energy is interrupted or cold persists longer than expected, the structure itself offers little resistance. The frontier approach shows that warmth is not about excess. It's about control. Controlling where air moves, controlling how much space needs to be defended, controlling how fast heat is allowed to leave once it's earned. This doesn't mean modern materials are useless or that progress was a mistake. It means resilience requires different thinking than convenience. Systems built to endure scarcity behave differently than systems built around abundance. The cabin proves something simple and uncomfortable. A structure that asks more from its builder can demand less from its fuel. And a building designed to survive failure will always look inefficient, right up until failure arrives. That understanding hasn't disappeared. It's just been buried under assumptions that worked for a while. And the longer extreme conditions return, the more clearly those older priorities begin to make sense again. Frontier cabins stayed warm at minus 30 degrees Fahrenheit, not because they produced more heat, but because they refused to let it escape. That distinction is easy to miss in a world where energy feels unlimited and systems promise to correct every weakness after the fact. But history shows that warmth earned slowly and held carefully outperforms warmth pushed constantly into a leaking space. As winters grow less predictable and energy systems more strained, the difference matters again. Structures designed to survive the worst night behave differently than those designed for average comfort. They don't rely on constant input. They buy time. They tolerate interruption. They fail slowly instead of suddenly. This isn't a call to abandon modern homes or return to frontier life. It's a reminder that progress often trades endurance for convenience, and that trade isn't always visible until conditions turn harsh. Efficiency isn't only about better materials or stronger machines, it's about understanding limits and designing around them. The Frontier cabin didn't defeat winter, it accepted it, narrowed its reach, and worked within it. That approach kept people alive when fuel was scarce and cold was relentless. So the question isn't whether we should live like pioneers. It's this: what other systems did we abandon? Not because they failed, but because they demanded patience?